Welcome to episode 15 of Writing a 6502 Assembler in Assembly Language. This is actually the second time I'm recording episode 15 because when I recorded it last time, by the end of the time, I was really dissatisfied with the code I'd written. So what I'm going to do today is basically delete it all and go back. In episode 14, I started working on the subroutine to look up symbols in the symbol table, and already the beginnings of the problem were there, which is that I was using the technique of self-modifying code, and it turned out to be the case that I had to keep copying pointers into new parts of the code, and it was just kind of a big mess. So I'm going to not do that. Instead, I'm going to use pointers in zero page to go through the symbol table. There were a couple of other things, however, in the episode 15 that I recorded that I will not include as part of the series that I should talk about here. First off, there is the symbol compare subroutine. This subroutine compares the symbol, which has been scanned by the scanner, which is at location hex 200, with one of the symbols from the symbol table, which the address of which will be put right here. And originally I had this, it was very much like this key comp function, which it compared the two until there was a null, a terminating null at the end. However, the symbol table entries actually don't have a terminating null, or at least don't necessarily have a terminating null. They are allowed to be 12 bytes long with no terminating null. So actually, the comparison simply has to go here until 12 bytes have been compared. So what this will do is this routine will compare the name, which has been read by the scanner, with an entry in the symbol table, and if the first 12 bytes are equal, then they will be considered equal. For example, the symbol here, which is read by the scanner, the name read by the scanner, will be null terminated. And the idea is that when it's compared against the symbol table, here, let me pull up the symbol table, these things will actually be zeroed out. So if I have, my sub is 5 characters, so that means there will be 7 more bytes in this thing. It would be like 1, 2, 3, 4, 5, 6, 7. There would be, so here's 12 bytes in the symbol table. So if the scanner reads my sub with a null terminating character, it'll get here and say, okay, good, that's a match because it matched here. But if it doesn't have to be null terminated, if it turns out that the symbol or the name read by the scanner is 12 characters plus a 13th byte, which is the null terminating byte, or I suppose if it's 15 characters or 16 characters long, then it can match a symbol here as long as the first 12 characters match. That's the idea. And that's what this is supposed to do, right? So it's getting a byte from the table, it's comparing it to, I'm getting a byte from the scanner, from the name that the scanner read here. It's comparing it to a byte in the symbol table, of a symbol in the symbol table. If they're not equal, it goes down here. If they are equal, it increments x and checks to see if we've done 12 already. If it has compared, if there's not done 12, it goes back here and checks for another one. If it has done 12, it's going to load A with 0 and return that to show that that the two are equal. Now, I was just thinking, the name here stored at hex 200 is not necessarily 12 bytes long. That's a name in the a symbol or name in the thing, it could be like this: SYMCMP null byte, right? And so whereas here in the symbol table, if that one has already been entered, it would look like this: SYMCMP, and then 1, 2, 3, 4, 5, 6 null bytes. So it actually would be wrong if after it gets a null byte, it should say, okay, that's a match, right? SYMCMP with a null byte should be a match to this. It shouldn't have to compare all 12 bytes. And it looks like this code here does indeed compare all 12 bytes. Oh, no, it doesn't. Yes, it does, right? Let me just be sure about this. Okay, so get the null byte at the end. Okay, it comes out equal. So it's increment x, compare x to 12. If it's less than or equal to 12, thank God, there is no simcomp 0. Presumably that's supposed to be simcomp 1. So I screwed up more than one thing in the last episode that I will not be actually uploading. Well, maybe I will upload it, but it will not be in the playlist. It'll be just something you can see if you want to see me writing code that turns out to be really unwieldy and that I'm going to replace. Okay, if it's less than or equal to 12, go back up here. Oh, I see. That's not right either, right? Because actually I need to go up and get the next one here. So this thing just was not really ready for prime time anyway. All right, if x is less than or equal to 12, I'm sorry, if x is less than 12, not equal to, less than 12, go up here, get the next character from the name read by the scanner, and compare it against the name in the symbol table. The thing is, though, I have two choices. One, I could make sure that this always has a bunch of zeros after it. That is the symbol here. If that's the case, then it will always match the symbol if there are a bunch of zeros after it. But actually, I think once there is a zero here, that's the null termination for this name read by the scanner. As long as there's a 0 here also, then that should be a match. So I'm going to have to go back up here and put back in something like this right here to check, to make sure that I quit after checking null byte. Okay, so we take that and we put it into y. And then we can look right here, because here these two things are equal. If we'll compare y to 0. If it's equal, then we're done. But the thing is, where we need to go is we need to go right here. Well, we could do it like this. All right, let's do it like this instead. What we'll do is we'll, at this point, the result of the subtraction was 0. So that means that these two bytes were equal. Let's just move y into A. That will set the flags. And we can say branch if equal to simcomp2. That should be fine. Okay, so here's what we're doing now. When we enter simcomp, we first load x with 0. X is going to be indexing through both the name that the scanner has read, plus the symbol in the symbol table, a pointer to which will be put right here. Okay, so we get the first character, we store it temporarily in Y. We subtract the character in the symbol table from it. That's a way of doing a comparison. If the result is 0, then these two things were the same. Those two characters are the same. If the result is not 0, that means they were not the same. Therefore, this name is not the same as this symbol. And we'll just go down here and return the result of this subtraction, which is not going to be 0, as our result. A non-zero value in A, meaning it's not, they didn't match. This name here and this symbol here did not match. Otherwise, if the two characters did match, the byte from here and from here did match, we move that byte that we just compared into A, and we say, okay, if that byte we just compared was a 0, right, then we're done, because that means we just compared the null at the end of this name with one of the zeros, well, would be in this case like with this one right here, right, with that one. And so those two, that means our name is equal to the symbol. So we can go ahead and exit with a 0 in A, meaning it matched. Otherwise, we increment x and we compare x to 12. If x is less than 12, we just go back up and compare another character. If x is equal to 12, then that means that we have matched 12 bytes from this name here, read by the scanner, and all 12 of the bytes in the symbol table text field match. They're all the same. And then we'll call that's a match. If that's the case, we'll load 0 into A to make sure we're returning a 0 in A, which means these two things matched, and we'll go ahead and return it. So this sim_comp subroutine, first off, basically does kind of a normal string comparison where we're comparing two strings, and if they have null at the end, they compare, if all the characters are the same plus the null at the end is the same, it's a match. They're equal. But also, it will just stop after 12 bytes. So, for example, suppose that we had a symbol called this is long, or this is a long S, that's 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So these 12 bytes fill up this text field completely. There's no room for a null byte, but that's fine if in our source code we have a name which is this is a long symbol, which would be another 5 bytes, 17 bytes total plus a null byte at the end. It would still match this because the first 12 bytes would match, and that's enough. We'll stop at that point. So you can basically write symbols or names as long as you want to in your source code, but only the first 12 bytes will be considered. Anything beyond that will be ignored. Okay, so a symbol called this is a long symbol, and this is a long whatever, something that starts with S. This is a long symbol, this is a long strudel. Those would be the same symbol as far as the assembler is concerned, because the first 12 bytes would both be the same. Okay, so that looks better. I was expecting that to be already correct, but it looks like that now at least is what I want. The other little change I made in the code that I am now going to throw away. I mean, I'm going to throw away the episode or the installment I recorded. But the code was to go ahead and, if malloc fails, which means that we don't have room in a break, right? So we're going to get our break value, which is the last address or the next address in memory that we would have available to us for allocating more memory. Okay, and we're going to compare to the IO buff, which is IO buff, if you remember, we have IO buff 0, IO buff 1, IO buff 2, IO buff 3. These are 4 IO buffers. They are 1 kilobyte each long. that are used to handle open files, and it's related to the ProDOS disk operating system on Apple IIs. And so at the moment, I'm thinking I might need up to 4 buffers. So therefore, I've reserved those 4 buffers, but they're at the very top end of memory, just underneath ProDOS itself, so that if our break, which is the next location we can allocate memory from, is equal to IO buff, then in that case, we've run out of memory. So we're comparing it. Here's compare. We take the high byte of IO buff and comparing it. We take the high byte of the break value and compare it to IO buff. If the break value is less than IO buff, that means okay, good. We still have space available. If it's greater than or equal to, then what we're going to do is compare the low byte. And in fact, because we're allocating 32 bytes at a time, it's never actually going to be greater than, it'll just be equal to. Like when we're about to run out of memory, then the high byte of the break value will be equal to the high byte of IO buff, the address of IO buff. And so what we'll do is go ahead and check the low byte. And if the low byte is less, then we still have room. Otherwise, we've run out of memory and we're going to have a fatal error. And we'll just do that right here in malloc so that we can, for the rest of the code, we can assume that malloc will always succeed. It will always give us 32 bytes of memory. And because if it doesn't succeed, there's going to be a fatal error and the assembler will just crap out with an error, mem error. So anywhere we use the malloc subroutine, we'll just assume that that everything worked well. We don't have to worry about anything. Okay, so that was a small change I made in that episode I recorded, but that I'm not going to put into the playlist. The rest of the episode was looking at this lookup subroutine, and if you remember, in episode 14, we started the lookup subroutine, and we did some code to check to see whether or not a symbol is found in the symbol table. If it is, we looked along this list of symbols to see if we can find it there. And that was all in episode 14. In episode 15, we had the code that I wrote that I'm about to delete basically said, okay, if we don't find the symbol in the symbol table, then we need to actually add the symbol to the symbol table, which involves using malloc to grab 32 bytes of memory to make one of these blocks and putting the symbol in the correct place there. And that code all starts at lookup 5, I believe. So all this stuff is I did in episode 14, and this is the stuff here that I did in the soon to be no longer this episode 15. And it's all using self-modifying code. And if you see here, here's a place where I had to copy a pointer to there, and here's a place I have to copy a pointer, and here's just copying a pointer from one place to another so I can use it. That just really rubs me the wrong way as being not a good way to do this. So what I'm going to do is I'm just going to kind of rewrite the whole thing. I'm going to go up here, and first the part that hashes the symbol, I'll keep that. So here's where that is. Okay, we put a 0 in X and A. Okay, we get our character from the name. If it's the null, then we're done. We add it in there, increment, and then go back here, and we're just adding up all the characters. And then when we get here, we mask off the top bits. That is, we make sure that the value in A is between 0 and 63. And because we have 64 buckets here in our symbol table, each of which is a pointer to a linked list of symbol entries. Okay, and then we multiply it by 2 because each of these is 2 bytes long. That gives us an offset into the table. And we put that offset in X. All right, and then we check to see if this entry is null. If it's null, then the symbol is not in the table. We do that by getting the high byte of this entry right here. That's why it's +1. It's the high byte of the entry. If it is 0, then this entry is null. And that means the symbol is not in the table, so we go to look up 5. All right, and then at this point, if we don't, we start storing this pointer that's here into various places in the code, like lookup 2 + 2, which is down here, right? And we also store it in the symcomp place up here so that we can compare it to our symbol, our name. And this is the place where I'm going to go ahead and just delete all the code. All right, so here it goes. Goodbye. Goodbye, ugly code. Don't need you anymore. All right. And yeah, there's the memory error. That reminds me of an anecdote I saw about Ken Thompson, who wrote the Unix operating system originally, saying that in one of his most productive days ever, he deleted several thousand lines of code. Yeah, and sometimes that's just the best thing to do. Right, so what I'm going to do instead at this point is I'm going to use a 0-page pointer. And I think what I'll probably do is actually just go ahead and reserve this, the space for the pointer now. So I will take locations, actually I'll put 51 in there first. Locations 50 and 51 I will use as a pointer. So I'll go ahead and push those onto the stack, and now they are available for me to use without any worries whatsoever. I mean, this is just the ultra safe way to do this. Otherwise, I could just go dig through all the documentation and find some locations which are not used by the operating system and not used by the ROM code and all sorts of stuff like that. But that's a pain in the butt. I prefer just to push it onto the stack, and then I know it's available for me to use. I just have to restore it before I exit this routine. Okay, so I'm now looking at this pointer here, and that is, as I just said, it's this pointer here we're talking about, or this one here. It's one of these pointers in the symbol table. And I'm going to go ahead and store that in my location, my 0-page location. And then I'll get the low byte and store that in my 0-page location. So now I have a pointer in 0-page locations 50 and 51, well, hex 50 and hex 51, that points to this block here. And it actually points not just to the block, it points to this first symbol, the text of the first symbol stored in this block. Remember, there are 2 symbols in each block. 15 bytes here, 15 bytes here, 2 bytes for the pointer. So 32 bytes for each block. There are 2 symbols, possibly 2 symbols in each block. Okay, so now I have a pointer here. All right, so I do need to check and see now if this, I'm pointing at this block, but I'm also pointing at this text here, so I need to see if this name that the scanner has read is equal to the symbol. So I'm going to use the symcomp function for that. And I need to put things in simcomp 1 plus 1 and plus 2. Okay, and I could just store them right here, but and I may well end up doing that, but for the time being, what I'm going to do is actually just treat this as a break in the program, because this might be the top of a loop, and I'm just going to load these two and store them in the appropriate place. All right, and then I will jump to simcomp. Now, if the result of this, if what's in A after this call to the simcomp subroutine is 0, then they matched. And yeah, I'm pretty sure the flag is actually already set. The 0 flag would be already set there. So how do we get there? They're not equal. So yeah, okay. It's equal to 0 flag. Load 0. Oh, yeah, so the 0 flag should be set just fine. So I don't actually have to do a comparison. I can just go ahead and say branch if equal to 0 to found it. And I've thrown away all my labels, so let's just call it, I don't know, lookup 4. Lookup 5 up here didn't find it, right? We know it's not there. So lookup 4 will be found it, and this pointer at 0 page locations 15 and 51 is pointing to the symbol entry. Now, if we didn't find it, what that means at this point is that this does not match the name that the scanner just read, but this one might, so we need to check this as well. And if there is no symbol here at all, because we haven't used this slot yet, this will just all be zeros, because my malloc subroutine is actually more like a calloc subroutine in that it 0 clears everything. Right? Here's where it does that right here. It clears all of the allocated memory, which is every time is a 32-byte piece of memory. It clears it all. So if this is not used yet, it will just all be zeros. So we're free to just go ahead and call the symbol comparison routine on this one. If this one doesn't work, we can call it on this one. All right? And the way that we need to do that is we need to, this address of this thing here is 15 bytes after the address of this thing. So we're going to have to yeah, I think we better do this. Okay. All right, so we take the low byte, we add 15 to it, and store that in simcomp 1 plus 1. And then if there is no carry, then we can go down here. If there is a carry, I think we just do it like this. We can go ahead and load, after we've added 15 to the low byte, we can go ahead and load the high byte of the pointer. That doesn't affect the carry flag, so this branch here will still work as we want. And we can just go ahead and and increment A, but in the 6502 we can't actually increment A directly like this. So we'll have to increment A by adding 0 to it, which at this point, okay, what's, let's just forget that. Let's just do it like this. Just do the full 16-bit add. Okay, so take 15, add it to the pointer, the low body of the pointer in 0 pages 1551, store it, load 0, high byte, store it. All right, so what we're doing is while the pointer in the 0 page is still pointing up here, we're adding 15 to that and storing that to test in the simcomp routine so that we can test this one without moving the pointer. The 0 page pointer is still pointing here. All right. And maybe I don't want to do that actually. Yeah, maybe I don't. Because I need to know whether I found it here or found it here. Right? So yeah, of course, this makes me think that maybe I want to change this simcomp function also to use this pointer that I have here, because I have a pointer in the 0 page. So why am I not using it in my subroutine that actually compares the symbols? It seems like I ought to, right? Because the only place that this simcomp subroutine is going to be used is right here in the lookup function. So if I were to do that, then I would change this. This would be changed. Don't think I'd even need the simcomp1 label at that point. Sorry, there we go. Like I would be doing that. That means I couldn't use Y for this thing here. I would have to do something else, like, I don't know, put it on the stack would be fine, I guess. That would work. Okay. And in that case, I probably wouldn't want to use X here. I would want to just use Y. Right? That would make sense. So do like this, push that. Okay, get rid of that. All right, and you do that. If they're not equal, go down here. Otherwise, make sure see if if the thing we just checked was a null. If it is, and they matched, then go down here. We're done. Otherwise, increment Y, not X. Compare Y to 12, and go up here. So that looks okay. Okay. So now here I don't have to do this at all. I can just do JSR SimComp after I've stored my pointer, my symbol table pointer, that is this thing here, into the zero page locations 1551. I can call SimComp directly. I still have to add 15 to it. That doesn't change, because I need to point, instead of being pointing here, instead of my zero page location pointing here, it needs to point here. But I don't need this. That goes away. So if I didn't find it, then I add 15 to my zero page pointer. Oh, well, this is not going to work. I have to go ahead and store it back in there. Okay, so add 15 to the low byte, and then add 0 to the high byte. Any carry will come across there. All right, and then compare. That's comparing now the second one here. All right, and if I found it, great. If I didn't find it at this point, then I'm pointing here. What I need to do is get this thing and put it in my zero page location to make a new pointer to the next block of the list here, if any. I mean, it could be a null, but I just need to take this information, these 2 bytes, and put them into my zero page pointer. And to do that, at this point, the zero page pointer is pointing here. So plus 15 would be here, right? Because this is 15 bytes long. So plus 15 are these 2 things here. But I don't have to actually add it like this. Instead, I can just use the Y register. Okay, and I can get, that gets the low byte of this link here. All right, and I'll save that next for just a moment. Increment Y. And that gets the high byte of that thing. And I can store that in 51 and then store X in 50. So what I've just done is I have taken the pointer here and stored it into my zero page locations 50 and 51. So now what that does is, previously my pointer, my zero page location was pointing here, and then I advanced it to here because this didn't match. And now I have just advanced it to point to the next link in the chain there. Okay, and of course, kind of the thing I need to do now is make sure that this is not null, because if I just copy a null in there, I'm done. And I think what I'll do for that is, here I'm getting this right here, this code here, I'm getting this byte here and checking it for null before I move this pointer into zero page. In fact, I ought to move this pointer to zero page first and then check it. So instead of, when I do this TAX here, what I should do here is, first off, just load SimTab X and store that in the zero page location. And store that in the zero page location. All right, and now, right, I just stored the high byte in there. So the high byte is still an A. I can say if it's equal to 0, we'll go look up 5, because if the high byte is 0, it's a null pointer. All right. The reason for that is because, right, I have the same situation here. I've just updated the pointer here in my, I've updated the zero page pointer here by saying whatever is here is now in the zero approach pointer. So my zero approach pointer is now pointing at the next block here. And I can just go straight back up to this code here, right, to check and see if I have found it. And the only issue is here I've loaded the low byte. Now I'm loading the high byte of that pointer, and I'm storing it and storing it. The storing of it, this will set the zero flag if the high byte is 0. The storing it won't change the zero flag. So all I have to do is, yeah, actually at this point, I don't really need to jump back up here, do I? Because I already know whether it's 0 or not. I can just say if it's equal to 0, I will go to lookup 5. That means I didn't find it, because what happens in this case is I'm looking, my zero page pointer is pointing to one of these blocks. I check this one, it doesn't match. I check this one, it doesn't match, and this turns out to be a null, just like here, this situation. And that means I've checked the entire chain and the symbol is not to be found. That means the symbol does not exist in the chain. Yeah, the symbol does not exist in the chain. But that's actually a small issue there too, because what I'm doing is in that case, I have taken this pointer and stored it in my zero page location and then said, oh, it's null. That means I didn't find my symbol. But what I would really like at that point is I would really like to have a pointer to this block right here. I would like to retain the pointer to this block so that I can add a new block onto it. So probably I should check this pointer without actually storing it in the zero page location. That is what I should do. So what I'll do there is instead I will load y16 here. Let's just get rid of this. All right, the reason I'm loading it with a 16 is because the zero page pointer is pointing here at this point. And plus 15 is here, plus 16 is the high byte. Okay, so if this is 0, if this high byte is 0, then we're at the end of, that means that this is a null pointer, and we're at the end of the list, and the symbol has not been found. So we can go to lookup 5. Okay. So the symbol is not in the list. Okay, and otherwise, this is not a null pointer, so I'll go ahead and move that into X. I'll decrement Y. I'll get the low byte of this pointer, and I'll store that in 50, and I'll store X in 51. So that means this is not, when this is not a null pointer, like in this case, I go ahead and store this pointer into my zero page pointer, so my zero page pointer is pointing here. And then I can go back up to here to check and see if the symbol is located in this new block. So I'll go here. All right. And I think I have to do a jump there because don't have any other, I can't be sure of any other conditions, so I have to go up here. Now, That means this stuff I just did up here was not strictly necessary. It's not really that big a deal. So what I'm doing here in this case, what I've done is I've moved this pointer into the 0 page, and if it happened to be null, I'm going to say, no, I didn't find it yet. Yeah, that's actually a different situation. Like if this pointer is null is a different situation than if this pointer is null. Because if this pointer is null, I already have some things in the list. I have at least one block in the list. But if this pointer is null, I don't have any blocks in the list. So that will actually have to go to a different location. And I probably can just go ahead and, I think it's good to just go ahead and let's just call it lookup 6 for now. All right, and then store in 51. Okay, so I've gone back to kind of what I had before. I get X has an offset into this list of pointers here, this vector of pointers. And I look at the high byte of the entry I'm looking at. If this is null, then this is a null pointer like this here, which means I'll go to lookup 6 and not in symtab vector. All right, if it's not null, then I'll go ahead and store the pointer that's here into my 0 page locations, which is what this does, and then I'll start checking. All right, if we get a null down here, not in symtab vector, so right now lookup 6 is going to be the label that means we got a null here. Lookup 5 is going to be the label that means we got a null here. And those have to be handled slightly differently because when we get a null here, we have a 0 page pointer in 50 and 51 that points to this block, and we can use that to, you know, make a new block and hang it off the end here. In this case, we don't have that. When we have a null here, we don't have a valid 0 page pointer at all, and so we have to do something about that. We don't have any blocks here. We're going to make our first one, our first block, you know, first 32 byte block of symbols attached to this pointer here. Okay. So that all actually looks pretty good. Lookup 4, which is our label for we found the symbol. What that symbol does, that's when we go to lookup 4, we have our 0 page pointer pointing at either this one or this one, which is beautiful. That's exactly what we want because that means we can return the value of that 0 page pointer as our token value because we're going to return the token which says this is a name, a symbol. And as the token value, we will return a pointer to this symbol or to this symbol. And that's what our 0 page pointer points at exactly. So that's very nice. That's exactly what we want. Okay, so all we have to do here, in the case of we found it, is that we can load this 0 page pointer and store it into the token value. And then we have to restore the 0 page locations, low byte first, high byte next, and return. I think that will be correct. Now let's take care of the situation that the symbol is not in the list. So the symbol that we got that was scanned is not in the symbol table, and particularly it hashes to something to an entry here which has a non-null pointer. That means there's at least one block in this linked list of symbols, but we've searched the entire linked list of symbols and didn't find the one that we currently have. So that means we're going to have to add another symbol to the table, to this list. And we have two cases. We have the case that this is we actually have two cases to consider. We have the case that this one did not match and this one did not match. This did not match because this is all zeros. This symbol table entry here is actually available. It's free. We also have the case that this did not match and this did not match because these both are used. These symbol table entries are both used, but then here there's a null. So we have to look for both of those possibilities. Okay, so now when we create one of these, when we allocate one of these blocks, there's always going to be at least one valid symbol in there. So we just need to pay attention to the case that this did not match because it's an available entry. It's an empty entry. It's all zeros here, right? It could be like this, for example. Right? It would be just like that. That's what it would look like. This is used, a pointer to the next block in the chain. This one's used, this is not used. Yeah, but sure, this is null, but that doesn't matter because this one's not used and we can use this. How will we know that that's the case? Okay, we compare, this is where we're comparing the second of the symbols in the block, this one here. And it does not match at this point. So what I'm doing here, the first thing I'm doing now is I'm going to say, okay, it doesn't match, so let's try to follow the chain here. But we actually don't want to do that. We first have to check and see, is this an available space? Okay. Right, so we're actually pointing at that space right now. So we can, our zero page pointer is pointing here. So we can actually load a 0 into Y. And when we do this, we're getting the first byte here. If that first byte is 0, this is an available space. All right. So if that's 0, we'll go to look up 3. So we have an available entry in one of our blocks. Okay, so this is the situation that we didn't find it, we got the pointer to the next block, we didn't find it, but this one is available, and so we're going to use it. I'll just leave it like that for now. If it's not available, that is to say, if when we load this first byte, it's not 0, that means this one is also used. In that case, we have to go ahead and get this pointer and move it to our 0 page locations, as I said before, and jump back up here to search the next one. If that pointer turns out to be 0, we'll go to lookup 5. All right? Good. I kind of can see that some of this code might end up getting moved around to different places, but in any case, let's look at this situation first. In this situation, we have our 0-page pointer is pointing here, and this is an available entry. So we're going to go ahead and use that entry for our symbol. Okay, so we have to copy our symbol into here. And we'll do that with the Y register. When we get here, we already have 0 and Y. In fact, we've already loaded that first byte into Y. But we load the first byte here into Y. That's fine. We have 0 and Y. That's all good. So we're going to get our symbol from there and store it there. Okay, if what we just copied was a 0, then we'll break out of this loop. Otherwise, we'll increment Y, and we'll see if Y is 12. If it is, we've just copied 12 characters already, because the maximum we're allowed to copy in here is 12. And if it is less than 12, we'll go back up to lookup 3. Okay. Now, if we did copy less than 12, we copied a null, right? We copied from the name scanned by the scanner into the symbol table, and we copied a null. We're going to go down to lookup 3a, and what we want to do there is go ahead and fill in the rest of the thing with zeros. Yeah, technically there should be already zeros there, because when we allocate things, they're cleared by the malloc subroutine, and we don't ever actually reuse these things, so it should be all zeros there anyway. So I think we're fine. We don't actually have to copy zeros in there because there are already zeros there. If I later find out that's a problem, then oh well. But looks like this can be lookup 3a. Right here, we don't have to actually do anything once we've copied the null from the name read by the scanner into the symbol table. We're good. Okay, it's like if we just copy in their name, we will now have the situation, right? NAME, and then we copy this 0, which is the null. We copy it in there, and the rest are already zeros, so we're fine. Okay, at this point, our 0-page pointer is pointing to this thing right here, which is exactly where we want to be pointing. We're going to want to put a type or a value in there, but at the moment we don't actually have a type or a value. The type is 0 and the value is 0 because the malloc subroutine cleared everything out. And that's fine. We don't need any kind of type or value at the moment. The value of 0 is fine because we're entering a new symbol into the table. It doesn't have a value yet. So we can just, actually we don't even need that. We can just drop straight down here and return that. So we've just copied the name that we have found, which is not in the symbol table, into this empty entry of the symbol table. The 0-page pointer, the 0-page locations 50 and 51 already contain a pointer to this thing. So we just drop right down in there and return it. That looks very nice. All right. Now we have the situation that we've got a null here and we have to allocate a new block. Okay, and let me just check real quick. When we allocate a new block, okay, we have the new block that we allocated in X and Y here, and then we use X, but then we reload X. So the address of the allocated block is in X and Y. That's what I thought. I just wanted to make sure. Okay. So when we come here to look up 5, this is the situation that our pointer is pointing here, and this was not empty, but our name read by the scanner did not match what was here, and then this turned out to be null. So what we have to do is allocate a new block and store it here. Store the pointer to the new block here. All right, our 0-page pointer is in 1551. That's fine. Okay. So we can just go ahead and JSR malloc. Okay, so now we will have the pointer to the new block in X and Y. And we will want to store those here. Our 0-page pointer points here. So, whoops. I think what we'll want to do is move Y to A, and then load Y with 16. Or, yeah, 16 is right, because we're pointing here. 15 is the low byte, 16 is the high byte. All right, and we'll store that there. Transfer X to A, which is the low byte. X had the low byte of the allocated space, the address of the allocated space. Decrement Y. Now we've stored the address returned by the malloc subroutine into this place right here. Okay, and we also want to take this address that we just stored there and put it in the 0-page location. Okay, this is the high byte, this is the low byte. So we can store that in, we store it here, we can also store it in 50. Okay, transfer Y to A. This is the high byte. We'll store it there, then transfer X to A, decrement Y, store that there. We need to get that high byte somewhere. Looks like the easiest thing is to push on the stack there. So we come back from malloc with the low byte, the address of the allocated memory. Low byte is in X, high byte is in Y. Move Y into A because we need to do this here. And then go ahead and push that in the stack because we're going to need it in a minute. All right, so get this here. This allows us to store that high byte here. Then get the low byte into A, decrement Y so that we're now pointing at the low byte here. Store that, and store that low byte in location 50. Then pull A and store that in location 51. That's the high byte we pushed here. And now at this point, we have the 0-page pointer pointing to the first symbol in one of these 32-byte blocks, and this symbol is unused and is all zeros. We know that for a fact because we just malloced it. We just allocated this thing. So then we can go here to this right to look, we can just go straight to lookup 3, because what this is going to do is this is going to copy the name from the scanner into whatever is being pointed at by the pointer in zero page location 1551, which in this case is here, right? And then once it copies that in there, it's going to return that. That looks beautiful. And this is why I am rewriting this code, because this is easy. This is simple. The way I did it last time was ugly and complicated. All right, so I will jump to lookup 3. Okay. Now we have one last thing to consider, and that's the situation where this is null to start out with. In that case, we have to allocate a new block and store the pointer here. Okay, so we found that this thing's null. So we want to allocate a block and store the block here, store the pointer to the block here. And what we can probably do is just go ahead and let's see how lookup 5 works. It calls malloc and stores it into, it's assuming that the zero page pointer is pointing here, and it stores it into that plus 16. It stores it into this location. I think perhaps it's best just to say like this: lookup 6 JSR malloc. We're going to have to save the X register though, because the X register is going to be trashed by that. And for us, the X register is important here, right? It has our offset into the symbol table. Okay, so move it to A, push it, JSR malloc, and now what we need to do is we need to store this pointer that we just got back from malloc. The high byte, let's see, I think we can move, we can pull. We can move the low byte of the address into A. We can, but we can't get it back there. Actually, I'm going to move this up here anyway, because it looks like it's pretty far away. Maybe we can go here. Okay, I have a little problem that this 5x here has to be saved. And I think what I'll do is I'll just save it directly into the code. So I'll go ahead and JSR malloc, and I can transfer X to A. So X is the low byte of the address of the allocated space. I can load X 0, and this is, actually I'm going to store the X that I need here. All right, and then I can store A, which is the low byte, into symtab X, and I can store Y into symtab plus 1X. All right, so what I need to do here is just, actually here, it doesn't matter fundamentally, but I think I'll go ahead and store it like this, 6A plus 1. So I'm taking this value of X, which is my offset, into the symbol table here, and I'm going to just store that right here, right there. I'm going to store it there. All right, then I'm going to go ahead and load the high byte here. If it turns out to be 0, I jump down here and I call malloc. I move the low byte of the address of the allocated space to A. I retrieve this value of X that I stored there, and I use that to store the address returned by malloc into the symbol table that is stored right there. Okay, and I also need to store that in my 0-page location. Right, so now I have a new block. I had a null. I now have a new block like this. I've adjusted this pointer to point to my new block, and my 0-page location points to the first entry in that new block. And now I'm ready to copy that in there, which super conveniently is lookup 3. I say super conveniently because I can just fall right into it. So lookup 3 is the label where I'm going to copy the name that I've scanned into the entry here, whether it's this one or any of them. Okay, so this is the case that I have to make a new, lookup 6 is the case that I have to make a new pointer here. I call malloc and I store the pointer that I get back from malloc into the symbol table, and I also store it into our 0-page locations, and then I just fall right into the code that copies it in there. And after I've copied it in there, it's the 0-page locations 1551 are pointing to the symbol table entry for the symbol, and I just return it. All right, and this is the case where this is null and I have to allocate a new block and put it in there. All right, that looks like I've really taken care of everything. So that should be it for the lookup subroutine. And it's much, much nicer than what I had before. I'm much happier with it. And next time, we'll have to test it and make sure it works. So until then.